All right, so we're gonna be discussing. I'll just place the notes here, all right, so that you guys can um follow along with the notes. So there's just one file notes, and I don't have a PowerPoint for this one. So super learning, right? Is that the correct spelling? Let me try and search it. It's just one key. All right. So what we're gonna be doing, right? What we're gonna be learning is one. So we have K and N, right? K to the nearest neighbor for supervised learning. Here in supervised learning, there's also K means, but this will be for clustering, right? So if you remember, I wonder if I still have that here. PowerPoints. Yes, here. So if you remember, I was sharing this one. Let's see. Yep. So we have two types. It's association and clustering for the unsupervised learning. So we're going to be doing that one. So the first one is K means clustering. Another one is the hierarch hierarchical clustering. Yeah, this is clustering as well. Another one is for PCA. And then the other one is isolation forest. So these are four of the most common ways that we can do it in a supervised learning. All right. So a rough preview of what K means. Um, Basically, you can group like group group objects or data into clusters, and then based on um numeric features. So if we have numeric features, we're going to be doing that one. The output will be it would look like uh points where everything is used to like group together, so in clusters. For high hierarchical clustering, what you would see here is something like how data relates to each other, and then the output would look like a tree-like structure. Now, of course, there's some math behind these things. So it's beyond the scope. If you want to really learn the math behind these algorithms, then you can go ahead and search for that one. But again, it's beyond the scope, and also it's also beyond my expertise. But in terms of how to use them, right, this one, then that's something that you can do. PCA, this is like a not really an advanced version, but a simpler version, sorry, simpler version. Um, for 2D data visualization. All right. Um, yep. And then the isolation from the name itself, this is used to detect, sorry, detect anomalies or outliers. So that's what we're trying to detect here. All right. So these are the rough descriptions of what each one can do. You can use all of them and then just compare the results, just like what we did with supervised learning, right? And then choose the one that uh, fits the best, right? And try to see if you need to adjust the features. What data should you be comparing with, right? Like if you were to compare. like those are example again last time, the flights, right? So if you were to compare the delay time and then the arrival time, like is there a pattern? If there's no pattern, then choose something else. You're trying to look for a pattern, right? And then you're trying to see if you can verify that pattern and see if uh it's actually true, right? And create a model out of it and maybe use it for future products or services in for the company, right? Um, so yeah, we're gonna be doing the same thing here in a supervised learning, right? So we're gonna start with k-means and then going down to isolation for the stalls. So by the way, I prepared a data set for this one. I'm not sure if I uploaded it already. All right, so it's not here yet. Let me just upload here so that you guys can have it on your end. Uh, I was looking around for some data sets, and this is what I got. Uh, this is a data set about cars, and then okay, so you guys should be able to see it now. Uh, on the LMS. So it's the cars data set downloaded. And it has some data about different types of cars, models, their torque speed, top speed, uh, no, not torque, just torque, top speed of gas type they're using, company, and so on and so forth. So we're going to be using that one, all right? Okay, so that's that. Download it if you have some time so that you can follow along. Let's see. So I just opened the file. So there are so company car names, basically their models, the engines, the battery type, horsepower, total speed, the performance, or basically like this is the acceleration, how fast it can go from 0 to 100. The prices, the fuel type, how many seats, and the torque. So these are the data available with us, right? So immediately you'll see that there's a mix of data that we can observe that point. So, all right, so going back here, the first is we're going to import canvas as and then raw as input. Uh, we process it. Import. We know. So what is this one for? Uh, I'll tell you later when. Okay. So the first part is student does. First part is So first part is we're gonna load the set, right? So I'm gonna say something like file path. Then since I already have it saved in my root directory, so I can just say rs.sv directly. Sure, for explaining and make sure you have the check. Next is I'll assign this one to rs f canvas. And since this is canvas, changing underscore cs method of the we're gonna pass the name of file path where it's located. Next is we're gonna pick what we're gonna say. So usually when you have your pick the set up the first time, uh if it comes from a different source, and you have to figure out it from it first. Otherwise, if it's something to make yourself, then you can just send it forward out. So in this case, this data set uses stateful prototyping. And so how did I figure this out? Basically, I use sales. I use a description on where I got the file. So usually just listed there where I got the file. Right with this. And then yeah, the coding is usually I think with another description so it's easier uh on those two. Right? Okay, and also since I'm expecting some errors on this one, and I can say on it, and it's, I'm just gonna skip the errors. Right? So just skip them. And hold on for your screen or make it. All right. Next is let's see. Uh, we're gonna assume, right? It's always good to assume that your data set has some empty cells, right? Empty cells, empty place. So what we're gonna do is we're gonna say parts df, right? And then we're gonna use the drop and a and then in place. Oops. And that's usually enough. And then it will replace those things with just some uh, uh, by the way, it will replace technical drop with those all right, step three, we're gonna have to uh, create a function, right? Yes, if you've opened up first, it's price. All right. So if you've opened first PDF, you will see there. Um, Although it looks confusing, but just separates them because there are columns, right? So you can't really go left or right on the output section. That's why they separated each one in very different groups. So this is the first three columns, the next three columns, the last three columns. So if you would take a look at it, um, we have a mix of text and numbers, right? So aside from seats and then maybe possibly prices, we can uh like just process them directly, right? Uh you know what? Maybe prices we need to actually remove the dollar sign, maybe the comma as well, so that it can be processed as what? As numbers, right? on camera. So we need to clean this data up, right? So this is one example where data is a bit messy. So you need to take that into account. And then that's initially the first step, right? Okay, so let's remove that. Okay. Let's create a, so I'm gonna name it clean and then clean numeric, right? And then what are we gonna pass here? So since this is a data frame, we're gonna be using a series. So series is just another or a column, right? So what does this do? Um, we need to return something, right? So after accessing the column, we need to return the same column with the same values, but it will have those texts removed, right? Like for example, the battery capacity, you need to remove CC, horsepower, HP, and so on and so forth, right? We need to remove those things, okay? So let's focus on the numbers for now. Let's do something else later for the series where they're not numbers, right? So we're going to have to find a way because whenever you're dealing with algorithms, right, you're going to be, um, you're going to have to find a way to represent those things as numbers. So that's what we're going to. But first, let's go to the easier. So the ones with numeric data. All right, so what are we going to do? So first is we know that we're going to return something. We're going to return the column itself. So we're going to say return PD, and then we have a method in pandas, and that's actually called to numeric, right? So you can search this one up if you have time to know more about it. But basically, from the name itself, it will just convert it to numeric, whatever data there is on that series. So we're gonna say the current series that we're using, or the current column, right? And then we're gonna use the as type, all right, method. Now the as type here converts everything to a string first, right? So why do we need to do that? Because we need to use it for string operations, right? So why do we need that? Because we need to points. So now that this is a string, we can now use string methods, right? And if you remember, replace is one of those methods, strings. Now, what do we need to replace? So using regex, right? We haven't really discussed this one, but we're going to be using regex. So uh, the meaning for this one is skip it, this one. Basically, it's some kind of filter, right? To filter to search for something, right? So say you have a sentence, you have this filter, the regex, and that you're looking for something like a date. So what would that look like as a filter? So you would tell it like it should be four numbers in a sequence, right? So any kind of match to that, it will retrieve that information, its location, and then um, you can do whatever you want with it, right? So we're going to be using regex, right? So if you remember, replace has two basic arguments. One is what do you want to replace, and what do you want to replace it with? So what are we looking for? So if you're looking for uh not numbers, we want to remove everything that is not a number. So comma, dash, HP, those kinds of stuff. Uh yeah, for each that one. Uh yeah, we need to do that as well. So Okay, so let's see. Yeah, I'm sure it's here. Was I able to share it here last time? Let's see why. So I can't seem to share it directly here in Zoom. Wait, let me check. I'm gonna try. We try. All right. Here's the link. Can you please tell me if you were able to download it? Uh, yes, it's the same file, sir. Yes. So it was just that Irma had difficulty with downloading it from the LMS. So that's why I also place it here and Google that, right? Okay. So, all my questions. Okay, so what do we want to replace it with? So we want to replace everything that's not a number. So how do you put that in regex? So we're just gonna skip this one. So it's we use brackets for regex and then we indicate the power symbol is up here. And then you say 0 to 9. So this will basically tell replace method to skip or look for anything that's not a number. All right. 0 to 9. And then what do we do? You put a dot here to indicate that anything that follows afterwards. So there can be as many numbers there are. So, like for example, here, so 3990. So, uh, yeah, as many as, and then after that, you indicated what you want to replace it with. So you're gonna replace it with just a blank, basically just removing it from the string. And then finally, you need to indicate that you are indeed using regex. So we'll say something like regex equals true. And then we're still in numeric, all right? And then there is a error here that I just, to avoid for now. So first, and then, yep, errors and then first. So that's usually enough. So I usually just avoid errors in the beginning, just want to see what the data should look like, right? With everything not included, like all errors and those kinds of stuff. So what you are left with is you're absolutely sure that it's clean data, right? And then you can just go back and see where those errors were, and then try to see if you can, uh, you know, try to save that data and then apply it or include it in your data. So, all right. So this is the function that we're going to use. So all we have to do now is apply this function to all the applicable columns, right? So we're going to say cars. We have, uh, let's see. So the first one is CC bad. Just to make sure that then steak and then clean numeric, right? And then what I will pass here is the same column, same series. So I should say cars underscore f and then this one. Uh, dot okay. So what are we doing? We're basically replacing the current column, but it's the clean version, right? We pass it to the function that we created, and then it will remove all of those unnecessary parts and then assign it back to the same sequence. So we're going to be looking at the same table. So all we have to do is just copy and paste this one uh, here, and then we'll replace this with what's the next one? Horsepower. Horsepower. It's capital C. Horsepower. And silence. Right. What else do we have? Total speed, right? Total speed. So space. Speed. This one as well. We talk. We have performance. So it's a complete, we have to copy the whole thing. Okay, we're going to go back to this one since it's the search and copy. Get it. Next is cars prices. Car prices. See, right outside. What else? We have torque, right? So we have process these all things, right? So assuming that there's no errors and assuming that we have the correct spelling, right? Let's see. After after cleaning it up, what could possibly happen? So let's see. What could happen is that you would end up with, see, we could still end up with something that is not a number, right? So assuming that there will be some parts where it's NA, not an AN, not a number. So we're gonna have to clean it up again, just like we did here. Okay. So we're gonna say cards. Why am I saying cards? Uh, no, cards. Cards. Yeah. I'm gonna say cars, yeah. Uh, graph NA. The first parameter for this will be subset. Uh, because why do we need a subset? Because we are accessing the whole data, but we're only gonna be these series, right? We don't need to look anymore at company names, car names, field types, right? We're only going to need to check again for these things. So that's why I'm using the subset parameter here. And then this is equal to a list. And I think we can separate it like this. Okay. All right. That's horsepower. Next is total speed. Next is performance. Next is prices. And then finally the score. All right. You see horsepower, total speed, performance, time, business to work. All right. And then one last thing. We would also be using let's see, in place is true. Place is assume true. So let's just hope that Python tells us well. This is easier to read. It's like this, right? Um, let's see what else can be added. I think that's it. So we can try and print cars data. Let's see what will happen. So let's try and compare it, right? This is before included. This is after. Let's see if we can compare it. All right. So one. No errors, that's good. So this is before cleaning, and this is after cleaning. So as you can see now, take a look at our battery capacity. So it's now in number format, right? Uh, point, this one, seats, we don't actually need to edit that one, and then we have the torque. Yeah. So as you can see, one of the cars has an insane price. Since it's very big. Uh, 1212, what's that? It's a Mazda 787B. It's a race car. All right. So that's why it is. Okay, um, okay, let's see. So it looks a bit cleaner now, right? You can actually see it immediately after running it. And yeah, it's clean because we are avoiding the errors. But again, what we're left here is the actual clean data. So we're absolutely sure that we can use this as is. All right. Next is what are we gonna do about the parts where there are words like this one. Okay. So we need to again find a way to represent these things as numbers, right? So that they can be used in our algorithms, right? So how do we do that? Okay. So this is a part where label encoder comes in, right? Now we're gonna be using label encoder to um convert the text to an equivalent number representation. That's basically what it's gonna be. So if they are categorical data, all right, they're gonna be represented by either one, two, or something that the model can understand and use to relate different parts of the data. Okay, so how do we use the label encoder? We are, let's see, we are gonna save it to a variable called encoder, and then this will just essentially call the label encoder. Sure. Next is we are gonna pass it the columns or the series that needs encoding. So it's the company name, the course name, the engines, and what's the other thing? Fuel types. So these are the things that we need to convert to numbers. So since we can just use a regular for loop for this and then a list. So for column in, and then it's a list here. We can put company names here. Sorry. And then car's name. I just write it down. Car's names. Engines. And then fuel types. By the way, if you have any questions, just raise your hand, okay? For some reason, my chat is not really pinging whenever you type something. So what do we do again? We pass each one to the label encoder and then let it do its job, right? So we're gonna say cars underscore df, and then whatever column we are working on with. And then we're going to pass it to the encoder using the label encoder. And inside that, there's a method called fit and then transform. So from the name itself, it's going to fit it back to the same series while transforming the data into something different. Okay, so we're going to say it's going to need just one argument. So that's just, it's basically asking what series is it gonna edit. So you can just pass directly here, cars, yeah, same thing, column. But since it's also a mixture of numbers, right? There are some numbers here, you have to make sure that it is converted first to a string. So we can use the same function as earlier. If you are using a series, right? This is a series, right? Where you're referring a column in pandas. So you can use the same thing as this one, as type. So we're gonna say as type and then string. So that should be it. Why do I have an extra? Okay. So that one, right? So after this, these columns should have number representations on them when we try and print them out. So let's try and see. Print use label to print uh colors. Yeah. Hmm. I think it's too long, right? Let's try and use just the first five cars. Yeah, just the first five. So that we can just quickly compare. A cars, the transport encoder. It's a wrong spelling. Encoder. All right. So before cleaning, after cleaning, it's another cars, cars underscore web. Before, after, and then there is a label and cooler. So, as you can see, right, from company names, Ferrari, Rolls-Royce, Ford, we converted them into numbers. The same with car names and the engine types. And what's the last one? Fuel types. See, so whatever combination that was, right, it's now converted into numbers, right? And yeah, right. So this is it. This is going to be the data that we're going to be using. So we're done prepping the data, and it's now ready to be used for all of our methods here. All right. Now, if we are to like discuss something, let's see. So if label encoder is still a bit confusing, right? Um, let's see. So we used something similar back then. I think it was in your question. Let's try and get this one. We used, it's not this one. Okay, I don't have it here. I think it's somewhere in my other device. Let's see. Let's see if I can still find it. Just to compare. The nerd question, Jupyter. No. Let's try it out of this one. Try to, I remember we are using something different here. Ah, okay. There we go. So, some people going back. We are using something different. So we use the one hot encoder, right? So one hot encoder and label encoder, okay, these two things uh, do the same process. They convert um, categorical data into number equivalent, right? But why are we using label encoder instead? So label encoder works best for unsupervised string, okay, because it's compact and more efficient. One hot encoder works with let's see, works with how do I explain this? no natural order, right? So if you have something like, actually, we can use the one hot encoder for fuel types because this has no natural order. Because what are the usual fuel types? We have diesel, we have electric, we have petrol. So those data, categorical data, they don't have a natural order, right? Like if you were to represent diesel with one, electric with two, right? It doesn't mean that electric is better than two just because it has a higher number. You understand? So it's there's no natural order between them. So one hot encoder could have been used as well for uh the field types here. But label encoder can also be applied in the same way. All right. Basically you're just gonna have to choose between the two, right? Um but for a rule of thumb, let's see. Basically, one hot encoder is used a lot for linear models, like for supervised learning. And then label encoder is used more for unsupervised learning. So just use that one as a basis for that. And don't try to mix them up uh, as early as, if you start your own projects, just choose one. And then if you're using supervised or unsupervised, then for unsupervised, use table encoder. And then for supervised, use the one hot. Again, they both do the same thing. If you want, you can compare the results with what effect one has on the other. But their purpose is just to convert them with their equivalent number. So I think that's it. Other than that, let's see what other examples can we find here. Oh, by the way, if you're uh wondering why it needs to be numbers, right? So I said earlier that algorithms are going to be used in numbers, right? So what are the numbers being used for? Basically, they're using some sort of distance measurement between the two data. So depending on that distance, they can somehow gauge their relationship. Are they related? Are they close to each other? Are they far from each other? Based on that distance. So that's the math behind it. Again, I'm not really uh too into that at this point, but at least you understand the concept that why does it need to be s- so they're using some kind of distance. If I remember, I think it was the Euclidean distance from what I read. So that's a higher form of math that I do not yet know how to do. But you can expand that one if you want. All right, so we are done with our data. What do we do next? So we're gonna go now and try and see if we can use k-means. Okay, so k-means here. We- this one. All right, we're gonna put something. Okay, display processing data. Oops. So why am I doing this? Because to minimize the screen, something like that. All right. So K-means, what are we gonna do? Um, We're gonna have to go back and say import pandas as PD, just to be sure, as PD, although this was already declared earlier. From SK learn, we're gonna import cluster, and then we're gonna import K, so the capital M. And then, what else? We're gonna import matplotlib dot pyplot dot pyplot as PL. So we're just gonna be using that. First step for k-means is that we're gonna be looking for numeric columns. So, uh, basically, we're searching for data types that are either integer or float. So we're gonna say x, assign it to x, and then parse underscore df. I'm using cars df. This is the one that we processed earlier, right? It's under cars df. So I'm gonna be using that one. And then, what do we do? We're gonna select the data types. This is a method under pandas, select the types, and then what are we going to include? We're just going to include all the columns that are float 64 and then int 64, right? Basically, it's just integers and floats. We're just doing this to make sure that they select the correct data. So if ever there's a missing column, then we know that we missed something. Then we need to go back to the processing of data and see where it made a mistake, right? So if we do that, we can try and actually print it out to see what it looks like. If it's actually the same, it's gonna run, and we can see that it is exactly the same. So that means that uh 30 horsepower, full speed, performance, cars versus torque. Is it the same line here? Scroll down. So we have, all right. So for K means we have excluded company names, car names. We have also included engines and let's see, fuel types, right? So these were not considered as numbers because they were just encoded by the label encoder. So let's see what will result after that. Okay, all right. So those are the data that K-means has selected. All right. Next is for K-means, you're gonna need two things. You're gonna need how many clusters and then the random state. So we're gonna assign select K-means and then stall out function it means and clusters, right? This is how many clusters you want. So this is something that you need to determine by yourself. How many clusters do you want your data to be separated? So if I say three, then it will be separated three. And then next is the random state. Okay, this ensures that the way that the clusters are being selected, the origin point, right, is the same every time that you run. So that means the result is reproducible. Okay. If you did not do this one, then it will be at random and then you will get different results. So that's why you get to put that in. A common question is how do we determine the number of clusters? Usually this is known because you have the data set already, right? And you can almost immediately see like how are you gonna separate this data into clusters, right? So let's say since we're dealing with cars, we're gonna be separating them into efficient cars, uh, luxury models, and then maybe race cars, right? So we can kind of expect like that kind of separation. So I'm expecting three for this one, right? But there are other methods available. There is, let's see, what other methods are available for triggering the cluster? Usually it's just because it's just, your understanding of the data set. So you're kind of guessing that this will generate like around 3 to 4 clusters. And then if it does not look like uh, good, the outcome, right, then you can just increase the number of clusters or decrease them as you see fit. All right. So we're going to be using three because I'm going to be assuming that the cars will be divided into three different types. So efficiency, the race car types, and then um, the one with either luxury or types that are used for businesses, the trucks. Yeah. So yeah, we'll go ahead and go with that assumption. Next is after assigning the key names, we're gonna create a new series in our data set. So we're gonna say cars underscore app. We're gonna create a new column. We're gonna call it cluster, right? And then we're gonna call k means again. And then we're gonna say dot fit underscore projects. And then we're gonna pass in X. Okay. So that's basically how you're gonna use it with chains, right? You let the algorithm handle how it's gonna use the data that it has basically in this one. And then see how it goes from there, right? So now we have a column for the cluster. Next is, of course, how to visualize this data, right? How are we gonna view this data? So we're gonna say PLT. We're just gonna use a regular scatter plot for this. But again, the decision ultimately comes to you on what would best fit the data or the feature that you have selected. So X dot, how do I say this? You're looking for Ivy lock and then 0. Next is this Ivy lock and then uh 1. C supposed to be 4 supposed to F Australian, yeah, C map. Uh, wait, okay. So what does this one do? Basically, we're trying to tell how to group them together. So X, right? This is the data of 0 and 1. Basically, we are selecting the whole series column of battery capacity and horsepower. So we are trying to compare, or in this case, I am trying to compare the battery capacity and the horsepower, right? I am selecting two features because this is a scatter plot. So I'm selecting two features and I'm gonna try and see how these two are related, right? So basically see here is what data are you going to be basing it with. So you're going to be basing it on the cluster because this is the result for k-means, right? So you're going to be basing it off what value there is, cluster. Um, and then CMAP here is just the color theme that you selected for the scatter plot, right? So yeah, I'm sure you guys still remember this one. So VLT X label, we're gonna put X label. We're gonna put here X and then columns. uh, 0. So that's basically the battery capacity. PLT.Y label, this is still X, and then arms of 1. That's basically horsepower, right? We can put in the title if you want. Let's see. K means plus 2, plus 2. And then finally, PLT dot show, right? So let's go ahead. This is the data again we're using. So there's around 1,200 rows. If we were to show export, there's an error. Okay, you show my numbers. This is in line 14. What's my error here? Plus 2, wrong. And there's another tab. Riddle. It's this one. All right. So what's this read? We have a warning. So returning the number of logical cores instead, you can silence this warning by setting Lucky Max CPU count for number of cores you want to use. So this is using Joblet. This is a library inside of sklearn, from what I know. So basically, it's trying to check your cores of your device, of your PC or laptop, because depending on how many cores you have, it's gonna use that all of those cores, basically. But since it cannot find the file specified for that one, that means it cannot read how many cores my device has. That means it will throw this error around. So instead, it's using the number of logical cores. So basically, it doesn't really affect our output in any way because this is just a warning. It's not an error. So you can just leave this one be if you have these kinds of errors or warnings. All right. Does anyone else have this error? If you're following along. All right. So silence means no. All right. So I'm gonna assume that no one else has this error. Only me. And this is our scatter plot, right? So we have battery capacity here and then horsepower here. Okay. So how do we read the scatter plot again? So let's see. Mm, wait, I think we're missing something there. We see the scatter plot, but we don't see the k-means. So let's show the k-means also. Print, uh, how do we call this? K-means cluster center, centers, right? And then we're gonna print, we're gonna access PD, the frame method, and then k-means, and then cluster centers, columns of x dot columns. So what are we doing here? Basically, I want to get uh the data inside of cluster here. That's also stored in k-means, right? So k-means cluster centers, and then for the columns, X column is gonna use the same columns as this one. All right. So basically, it's gonna represent the whole data into three clusters, but in table format. So basically, it's this one. Uh, I wonder if you see my mouse. Uh, Where's the annotate? Okay. Basically, it's this scatter plot, but in table format. So we have a scatter plot, but we don't have a table format. So that's what this code is for. So we're just accessing using the k-means cluster centers. Using this property, you can access it, and then assign the same columns as you were using with X here. So if you run this one, what you will get is the same data, but now it's grouped into three uh three clusters. So 0, 1, and 2, right? Three clusters. And now for each series, you will see the k-means for each one, right? So that's the data, and this is the visual representation of that data. So how are we gonna read this one? So let's start uh with the table. So each row, right? The row again is a cluster or a group of similar cars. Each column is a feature, right? And then each cell is the mean value of that feature along all the cars that's in this cluster. Okay. So the mean value is this one. All right. Now let's try and analyze this one, right? So we assumed that our data set can be divided into three clusters. So let's see. Um, for cluster zero, right, we can see that compared to this one and two, it has moderate horsepower. So it's around 8,000. It has a decent top speed. So that's around, it's a middle between the three of them, right? Two, one. And then acceleration here compared to the three is around 7. So it's somewhere in the middle. Three here is too fast, right? So 7 seconds, 0 to 100. The price here is, let's see, acceptable, right? It's around 1. So just comparing with the first digit, 1, 5, and 2, this is a lot cheaper. And then it has a torque of 1,000. So uh, basically, we can say that the zero, cluster zero is for regular cars, regular performance, right? Or at most, they are sedans that are almost to the middle end. Right? If regular is at the middle end, then sedans that are almost to the high end a bit. Uh, so again, whatever data set that you're dealing with, you're gonna have to be familiar with that data and with the jargon as well. So sedan, um, the hatchback, those kinds of terms, you're gonna have to be familiar with those things. A coupe. So yeah. What else? So cluster one, let's see, for horsepower is the one here. Cluster one has the extremely high acceleration. So this means it can go from, oh, there's a chat. I have so and I'm doing it now. Oh yeah, it's the same error as what I have. So that's just a warning. You can skip that one. Uh, since it's just a warning, right? So let's see. Cluster one, right? Looking at the data, it has the fastest acceleration. So it can go from 0 to 100 in 3.5 seconds. So that's very fast, right? It has, although a small battery. How do I know it's small? Because the exponent here is only up to 3. The exponent here is 7 and 6. So 0 and 2 has a higher capacity. Here, it's lower capacity. Um, what else can I see? The price is very big. It's insane. Exponent 13. So that's around billions, right? Or millions, I'm not sure. Um, but it's too big, right? We have numbers that are too big and too small as well. All right. Um, so we can say for certain that class one cars are near the sport type cars because fast accelerations with low battery capacity usually indicates that they're saving weight. So they want the car to move fast. From what they can see here on the data. Although some parts are not, um, does not coincide properly, right? Like the horsepower. You should be expecting that this is a high horsepower, but we don't see the data for weight, so this number might actually be big for sport type cars, but the performance and the dual speed actually match. It has a higher speed, right? Right. Torque also doesn't really quite match. Torque is how strong it spins, right? That's a torque, that's a spin usually. So let's see. Okay, maybe it might be the same with horsepower. Since it's small, it's designed to be lighter, right? Faster. So these numbers could be big in terms of sports cars. So, for cluster two, we can see that it has what a very high torque, right? So, in what applications do you usually need high torque, uh, high horsepower, right? It has a lower speed as well. Acceleration is also slow. So based on this data, right? Like what kind of cars usually have those kinds of torques? So from what that I can see is that these should be somewhat closer to trucks, right? Because trucks carry heavy things, so they need more power to spin, to move the car along, right? So if you need more power to spin, then of course you need a higher horsepower as well. But the trade-off is that the total speed is lower and the performance is also lower as well. Price range is about the middle, which is kind of understandable for trucks. And then the battery capacity is somewhat decent as well. So it's in the middle part. So yeah, we can expect that the heavy car types are clustered together in cluster two. All right. We can see these represented here in our graph. Uh, so we're not able to indicate which color is which. You can put a legend if you want, but basically we should see three colors. So it's green, I know not green. I forgot the other color for green is, but yellow, violet, and then there should be another color here for the third cluster. So what does this mean, right? We have to analyze. So we indicated three clusters. We should be able to see three colors at least, right? So what does this mean? So we have observed earlier that we have numbers that are too big. We have this one. It's really big, right? Exponent to the 13. That's a lot of zeros. If you were to compare this price with the other prices, this one will dominate. Okay, this one will dominate. So in whenever you're trying to run algorithms like this one, you also have to remember uh normalization, right? You have to normalize the data. so that they can each data set is treated fairly. Right now, we are treating this data set as some kind of like special because it's too high, right? The price is too high. Even the torque and horse speeds are high. So we need to normalize this data so that everyone is treated fairly, right? Um, so that's one thing that you should always watch out for. If there are data that is too big, or just for rule of thumb, whenever you're handling data, just normalize the data um, if you can, right? Just normalize the data to ensure that you're treating those data sets in a fair way. Okay. So what do we do? We can say right now that our output is still lacking, right? It's not fair, so to speak. So we need to fix something here in our data. We need to fix something in our data here so that we can normalize it. So we were using something similar before. It was the standard scaler. So we're gonna be using the same thing for this one. So we're gonna import a scalar key. So let's import scalar. This is the pre-processing uh standard scalar. Oh, no, wait, this is not it. Right? This is from a scalar and pre-processing and then standard scalar. This will be the same. We can leave this one as is. Then before passing it to k-means, we need to normalize the data first. So scalar, um, standard, scalar, um, and then assign it to a new variable. So since we're using x, we'll call this one x scaled. All right, and then we'll say scalar dot fit underscore transform has the data here of x, and then we should be good to go. All that's left is k-means here is still the same. We're gonna be using 342, but the fit predict we will be using the scaled version, the fair version. So x scale, right? Um, yeah, what else did we um, so whenever you use normalization, it won't be using the same values anymore. So what's gonna happen is we can't do it directly like this. We need to uh we need to get the inverse of this one. So whenever you normalize the thing, this is needs you need to remember this one because you're gonna be showing it in table format, right? So we're gonna have to convert it back to its original data. So you normalize the data, it's represented as a different number. After that, right, it's not gonna look the same number as before, right? Because it's being represented by something else, similar to what we did with the one hot encoder and the label encoder, right? But this time it's just the numbers um represented as different numbers again. So we need to make it transform back to its original data after so that we can view it normal. So we're gonna say uh cluster centers original. Let's say this original. So we can say scalar dot inverse transform. This is what the scalar uses to transform our data back to its original format. And then all we have to do is pass in the key means cluster centers. Because this is what we're using supposed to be, right? So since it was converted, we have to convert it back. And then all we have to do now, oh wait, this was simple. All we have to do now is pass this one, the original data, here. So basically, um, yeah, that one. And then it should print out the same thing as this one, right? You'll see later what happens when we don't do that. So right now, yep, we're still seeing the same thing. If you did not do that, right? If you let this be the same thing as before, but it was normalized when you print the data, it's gonna look something like this, right? Because this is what normalization does. It scales all the features to a different number, so 0 to 1, right? That's why we have 0 to 1 0. Sometimes if they're big, then it's represented as something else. But yeah, that's the whole point. You have to okay, uh there's no control Y. Where's there? Oh, here. Cluster sensors. Where's there no range? Okay, never mind. Okay. All right. As you can see, we have the original data back, right? And okay, now we are seeing three colors in our uh, scatter plot. So we have the violet, the green, and the yellow. So yeah, I was right earlier. It was green for Veritas. So let's see. Let's try and analyze it out. Um, so almost all the cars are within the 0.00 battery capacity, right? Um, let's see. So 0.25 here. So most of the cars that we have are around at this range of battery capacity. Again, we're only looking at two features, battery capacity and horsepower alone. So we're not um, trying to see the other features on how it affects them. We're just trying to observe two features, battery capacity and horsepower. So we can only see one extreme, and that was the one here in green. So this will be our outlier. Again, in terms of battery capacity versus horsepower. So what can we do with this data? So we can be sure now that we can profile cars that belong in cluster 0. We can say that they are now the standard, right? We can say cluster 1 is for sports cars, and then cluster 2 is for heavy trucks. Yep, that's like what we discussed earlier. Um, let's see. Hmm. Let's try and see the cluster summary. Maybe we can get something else on it. So the cluster summary is um, we can see the mean for each feature per cluster. So we can say print uh, cluster cluster sum. So how do we get the cluster sum? So we're gonna have to assign first the variable to this, and then cars. Yeah, gonna group it by cluster. So all the zeros are put into the same one, right? Zeros plus on twos. And then we get the mean. So the numeric underscore only, and with this one to true. And then we'll print this one out. Cluster summary. Let's see. All right, so cluster 0, 1, and 2. These are the means in terms of capacity and fuel type. Wait, cluster summary. Ah, okay, here. Fuel type and torque means places. Okay. Okay, so we're using the mean, right? So the average. We can now see that. Let's see. The car prices now on average is this one. Hmm, cluster two. Work is now 6. Okay. Although I said numeric only, it included the mean for the company names, cars, and engines. We can just exclude this one in our analysis and also for the few types. It got the mean, but these mean values are irrelevant because the data is um, not really used in this manner, right? You can't get the average of company names, so that doesn't make sense. So we'll focus again on the numeric ones. The car prices, it looks like the more expensive ones are now in cluster 2. The higher torques are in cluster 1 with a higher horsepower. And then, let's see. I think this just made it more confusing. We'll just use the uh regular cadence tool. I think using the mean just made it more confusing for us. So we'll stick to that one. Our final output will be the cars belonging in cluster zero are the regular or the standard cars. One will be for the sporty ones. Now the sporty ones are with a lower, lower, yeah, okay, so high performance and then high price. So this it's cluster two. Yeah, so high performance, high price, low capacity. So it's now in cluster two. We can now classify cluster two as the sporty cars. Cluster zero is with the high horsepower and the high torque. So these are the uh, truck clusters or the heavy duty clusters types of cars. And then cluster one is now for the regular or the standard car. Because this one has the uh average, so to speak. Yeah, so it matches the data. The clusters just switch around. So it's still the same tagging. We're still tagging the same names for the clusters. It's just that they switched clusters around after we normalize the data. So the most expensive one before was in cluster one, right? But now it's in cluster two after it was normalized. So you can see the effect of normalizing the data. Again, we can confirm that the data is more accurate now because we see three colors on our scatter plot, violet, yellow, and green. All right. So I think we can be satisfied with this output for now. Although we do need still to recheck our data. Like, I can see some parts where we can still improve our data, right? If you remember, there are let's go back here. There are parts in our data where something like this, 70 to 85 HP or 12,000 to 15,000. So it's not exact, right? So when you remove the special characters, what does this become? It becomes 70 to 85, right? So it doesn't make sense. So what this will become is 7,085 horsepowers. So technically speaking, our data is not 100% accurate because of data parts like this one. So we need to add a few more steps into our data cleaning. So either I think this would be easier to edit if you were in Excel rather than in um, using Python or in Pandas for this. So you're gonna have to mix it up, right? Like whenever you're cleaning data, you have to see which is faster if you were to use Excel for your data set, or if you're gonna put it programmatically, right? Directly into your program. Putting it directly into a program will make it automatic, right? Like any kind of data set that you give it, it's gonna remove those things and um get the accurate data. But again, in this case, I think it would be faster if we were to edit the data in Excel, right? Like separate, to use the dash as the separators and remove those data and then combine it back with the last text and the original data. So what you would be left with is just a single number, not anymore a range of numbers. So for me, right now, I think Excel is faster rather than we were to put it into code, right? And then, yeah, I think that's the only improvement we can get. So I'll leave that part to you guys. so that we can export a bit more. Other than that, what else can we improve with our data? That's the only thing that I can see that we haven't edited earlier. So it might also affect our final graph here. So since we have horsepowers that are too big, that's why we're seeing large numbers here. See, 350,000, 300,000. I was really wondering about this one earlier. Since, what's the unit for horsepower? Horsepower is HP, right? And then the other one is for, what's this? Battery capacity is in CC. So it's also rather quite large. CC. This is the original data. 1212. So I don't see any ranges in the battery capacity, but there might be ranges in other rows. So I'm guessing that's what we're trying to see here as well. Because right now the data really looks weird, right? With 350,000 horsepower. Is there, let's try and use a quick Google search. Cars with 350,000 horsepower. Let's see. All right, so I have a result here. Uh, let's see, BYD, the largest, is around 3,000 horsepower. So now we can safely say that even though we removed all the special characters, the NAs, the NATO numbers, based on this number alone, right? And the maximum number from what I searched here in Google is around 3,000 horsepower. 3,000. There's a lot of zeros here. So that means some of them, right, in some of our data has some ranges as well for um, battery capacity. So that's something that we can improve on in our code and in our data set. Um, yeah, so this is still wrong. Let's try and see. Oh no, wait. Let's discuss first, since we were able to like know how to get the k-means, right? So the only thing left is cleaning up the data. You can actually just do this one by yourself, right? We'll try and proceed with the other methods so that that way you guys you know how to do each and every one of these algorithms, right? So yeah, I'll leave that one to you guys as your assignment. See what it looks like after cleaning up the data. It's your choice if you want to use Excel or programmatically use pandas. I think using pandas would be a bit more complicated a bit, but it's really doable. So I'll leave it up to you guys. Okay, let's take a quick break. Anyway, hierarchical PCA and isolation forest uses the same scaled data that we're using in K-means. So since we have already scaled the data down, right? Um, Again, assuming that all the data is correct, just ignoring these things for now, so that we can have a proper result. We can just pass them directly to hierarchical, PCA, and isolation. So it's less code and more discussion on what makes them different to k-means, right? So let's have a quick 20-minute break. Let's get back here around 3:20. So have a good coffee break, snack, and I'll see you guys later. Okay? All right. All right. I hope everyone had a good break. So we went over it, but that's okay. We only have three more methods to discuss. All right. Can I get a confirmation that you guys are back? Quick thumbs up would be great. All right. Thank you. Okay. All right. So this is the part four. Here are the plus 12. All right. So how do we do with this one? So first is we're gonna have to start from declarations, right? So scipy dot cluster dot hierarchy. We're gonna import two things. So that is linkage. Linkage is what we'll use for the clustering. And then for the visualization, we're gonna use something called a then program. So this is usually what's used for hierarchical clustering, right? So first is we're gonna have to um build the linkage metrics. So basically we're done with this step. That is processing the data and then making sure that we have normalized the data. So we have done that one. If you guys remember, we used the variable x underscore scale. So we're going to be using that one here, x scale. And then after that, the algorithm will merge the most similar pairs step by step until it goes to the tree-like structure that I said earlier. So that is what our expected output should be, right? So um yeah, we'll just go ahead and use the data that we have. So we're gonna save it to a variable. We're gonna call it linkage matrix, and then we're gonna call the linkage function. It needs two things. First is the data that is in data frame format. So data frame data type, and then scale. And then the second is the method. So the method is we're going to be using the board method. So there are other methods for this. You can explore that one. So single is when you use single, it's based on the shortest distance between points. When you use complete, it is the farthest. Average, of course, is the average. And then ward here, it minimizes the total within cluster variance. So any kind of data that is continuous, right? Word is the best option for this. So our data is actually continuous data. So we're going to be using word, right? Again, if you go to the documentation for this one, there are examples there, guides on what data types fits what method best. So if you need more information, you can go to the documentation, all right? Um, And basically, that's what we'll do for the hierarchical. It's that easy since we're done with the processing step, right? We're just trying to implement it into the different algorithms that we have. So we're going to plot the dendrogram. So you got say PLT, that figure, big size would be equal 10 and 6. That should be enough. And then we're going to call the dendrogram. We're gonna pass in the leakage matrix here. We're gonna use labels on it. So the labels are gonna be from our data frame. And then let's see, company names, company names. So this is gonna be the x-axis, right? And then dot values. Next is the leaf rotation. So it's not, since there were a lot of company names, I'm guessing we can't even read the company names anymore, but it's a good idea to just rotate the leaf by 90 degrees. So the leaf is each and every point at the bottom of the x-axis. So if you rotate it by 90 degrees, the text will now be in vertical format, so you can um, read it vertically. So the data will be side by side, right? It's not too wide because the text is now vertically oriented. So, but since there are a lot, odds are we can't even read it anymore. So if I remember, there were how many? There were a lot of company names earlier. So yeah, we'll see. PLT title, and I will say hierarchical clustering, and PLT dot X label. What we'll put here is our company, and then PLT dot Y label. We'll put here distance, the same distance that we were using with k-means, right? So if you remember, the algorithm uses the distance, Euclidean distance, between two data sets. So based on that, you can tell how related two different data points are, right? And then plt.show. So this is all that we need. Let's okay. SciPy got cluster linkage and then go then draw then go then draw down. Not this one here. SciPy the cluster working is oh, okay, it's in line 8, sorry. Then program, right? Okay, company name, car company. Key error. This is on line 8. The error is on line 8, key error. So let's see. Mm, what's the company name? Company. It's not here. Company name. Yes. The well, all right, there we go. So let's get this one and this one as well. Okay. Now this is what a pentagram looks like. All right. So the first question would be, how do we read this one? Right? So um let's see. So each leaf, right? The bottom label is one car or one company, and they are sorted to how the algorithm merges them. So it depends on the entire structure of the dendrogram. So it's up to the algorithm to sort it out. All right. Uh, let's see. What else? So vertical lines, right? The vertical lines are the merges. So that is when the clusters are being joined. So every vertical line represents a merge between two cars or two clusters. Okay. The height of the vertical line shows how far apart the clusters were before they merged. Right? So the smaller ones have more similarities between, right? That's how I was trying to read. So the longer, right, the farther they are from their similarities. Okay. Um, what else? Each color represents a cluster based on the distance cutoff. Um, Colors are automatically generated unless you specify it. And then, yeah, so for example, this red one, these cars are considered similar enough that we can consider them to be one cluster, right? So all the cars here, we can consider them as one cluster. All the green ones, the orange ones, the purple ones, and then afterward it's the blue one. So as you can see, the blue one almost encompasses everything because it's the highest point, right? So that makes sense. Um, so now, if we want to like divide, right? You want to, let's see, let's say if you want to divide this by the distance, you can determine how many clusters, right? So if you divide it here, so it's going along this line, right? And it's intersecting these things. So you can count how many clusters there should be. So there's one, this is two, this is three, and then these two are the same, so it's considered as one. So there's around four clusters if you cut around this part, right? So you will see four clusters. The same thing here, four colors at the bottom, right? So that makes sense. Each label that you see below, right? We set it up to rotate by 90. And as expected, we can't read the labels anymore. There's just too many. So in order for us to read this properly, you would have to generate this one in a much bigger screen or one with a horizontal bar with it. So unfortunately, Jupyter Notebook can't do that one since the data is too large. We're gonna have to find another way. But the important part is that clusters. So this is what we should look at. Okay. Now, what is the difference between k-means and the hierarchical clustering? So for the K means you have to specify the K first, right? If you remember the K Remember the K parameter? It was how many clusters you think your data set will have. Whereas in hierarchical clustering, you can visually see immediately, right, how many clusters it can generate. And depending on where you're going to cut it off, it can generate into more clusters or lesser clusters, right? So it's going to be up to you how many clusters do you want it to be separated, right? What else? So in terms of a visualization, right? We were only using a scatter plot then. Um, but it was looking at only two parameters. It was not taking two features only. It was not looking at the whole thing, the whole data set, right? So um, let's see. In terms of speed, you saw earlier that there was a certain lag right before the dendrogram was produced. So that was just for 1,000 rows. If you have more than that, right? Um, this method actually takes more time since it's slower compared to k-means. So that's one of their difference as well. So um, when should you choose hierarchical clustering? It's better to choose this one if you want to know the relationship or understanding the whole structure of your data set, so to speak. If not, then k-means is usually uh, enough so that you can get the relationships that you want to, right? Okay, so what else can we do with this one? Well, we can put a line here to indicate what part we are cutting off so that we can say that we're using four clusters um instead of like they're gonna be asking how many clusters do you have, so we can say where should we put this one. If we're gonna put a line, we should put it here. So PLT dot um a x horizontal line and then y of 20. And then the color would be black. This is black. Line style would be around two dashes. And then the label would be well the cut line or cluster cut. Uh, that what else? So, all right, so yeah, that adds more depth to our visualization. So now they know how we arrived at four clusters. So this is our cutting line. Um, what else can we add here? Um, what if we want to know how many clusters there are in our data set in each cluster. So we can actually add something. It's called the F cluster. We can add this one. And then let's see, linkage. So after the linkage, then we pass in the cluster. clusters as opposed to F cluster, then what was the first? Uh, oh yeah, we pass in the linkage matrix on this matrix. We are expecting 4, right? That's what we do. That's T4. And then right trigger is max and S. So usually this is the default max cost. Uh, let's see. Cars underscore DF. We're gonna create a second cluster. Cluster 2 says we used cluster. There's an additional cluster column in cars DF from K-means, right? We added that one earlier. So we're gonna name it something else. Cluster 2, and then we'll assign here the clusters data frame. Right, so it'll be added to our current data frame for class cars DF. And after that, what else can we do? We can let's print it up for. So if we print cars store data, cluster two, and then the value counts. So this is the method to use in order for Python to count how many of your data rows fit to each cluster. So now we will see how many of them actually are to each cluster. So if we run this code, okay, so all right. So cluster two has for cluster one, it has 1,112, 75 for cluster one, 8 for cluster three, and 1 for cluster four, which is which one? So I'm guessing this is the 1,000 part. This is the 75, the 8, and the 1. Oh, wait, let's check. We need the color is different. You need to change the color. So we need to tell the graph to change the color since we are cutting it here. So it should not be violet and green. So we're gonna say color threshold, thresh, thresh. This will be the same number of the distance, so that's 20. Rush. So 6 clusters. 1, 2, 3, 4, 5, 6. But hmm, Give me a moment. What are you missing? Why isn't showing six colors? Hmm. We're gonna need to review a little bit. I forgot that there are other parameters for dendrogram. This is what I remember. And then should be four. Why do we have six colors here? Information and correlation. Let's try three. What would happen if we say? So since we're going higher, there should be fewer clusters. Try this one out. Okay. Right now, there's still five. Let's try 40. All right, so now there's three. I think that's too much. 35. So again, it's up to you really where you want the cut line to be. So if you want it to match exactly what we have here for 4, then we can just look for a threshold or a y distance where it's separated into 4 different clusters. All right, so I think this would fit. So one, two, three, and 4. Right. It still doesn't make sense, right? Because 112 material linkage matrix clusters equal. The count here is different. So I think it's safer to say that our visualization here is more correct than the one that it's counting. So we're gonna have to review this one and see what we're missing. Right now, it should be good, but the data here is not matching properly. So if it's 1112, then 75, then 8 and then 3. 8 and then 1. But this isn't 1. There's a lot. So this doesn't make sense. Huh. So if we set it up to 40, it kind of matches what data would we had with Amy's, right? Where there were three clusters, right? So this makes more sense if we set it to 40 rather than 20. So if we do this by threes, what would happen? 1187 8 and 1. All right. So there's something wrong with the F cluster on where I am trying to uh create a new column. So let's dispatch of this one for now, since this can make things confusing for us. I'll try to see if there are anything I can do at this later on, but what should appear here should match what we see in our graph, right? Right. So there's nothing really more to expand on this other than tagging the course with that associated category. So I'm assuming since this is fewer, this would be for our more pricey and fast cars. So the sports cars. And then this is, I think, for the trucks, the heavy duty cars, the heavy duty vehicles, and then these are for the regular ones. So there's a lot here compared to the other two, which matches the data that we had earlier with K-means, right? So we'll go with this one for now. And for the F cluster, I'll try to see if I can make it work. Um, Maybe the data is affecting the output due to the dashes. All right. So yeah, it's that simple for the hierarchical clustering. Basically, it's the linkage that's the most important, and the dendrogram. F cluster was just there to show you if it matches, but again, it did not. So that needs more work on our side. Again, you're gonna have to confirm the data always with what you generated with what you have. If it doesn't match, then you're gonna have to keep on going back and forth. That's okay, since it's part of the job. Um, right. We're done with key means and hierarchical. Let's go now to the next one, which is PCA, right? Uh, mm, yes, yes. All right. Now what is PCA? So PCA is short for uh principal. I use some code. Yeah. So this is short for principal component analysis. All right. So this is a dimensionality reduction technique. So what it basically does is that it takes a lot of features like based on this data set we have, horsepower, torque, battery, and so on and so forth. And what does it? It combines them into a smaller, new synthetic features, right? And we call those things principal components, right? So principal components. So exactly the same, but this one, see, principal components. Now, are these principal components? So let's say we have PC1, right? So PC1, principal component one, will capture the most variance of information in our data. So that's one thing. The other one, or PCT, for example, this will capture the most, uh, let's see, mm, let's see. Let's go here. So it's PC1. This is for most variance. And PC2, this will be uncorrelated to PC1. But this will also have to find the next most variance, right? So I hope you guys understand that one. Um, Basically, we're just going to be using two principal components for KCA, right? So it allows us to more visualize the complex multi-feature data into just something that's 2D. So everything that's all the data that's for that thing, right, is like considered when it's actually trying to compare it with another, right? So yeah, the variance in this case tells how much information the component can hold. So since this is the most variance, let's say if it had like horsepower, torque, CC, and for in this PC1, then those are the corrections that was stored in the PC1 variable. So let's go ahead and try this one out, right? So from sklearn, we call this one decomposition. It's under the composition, and then we're gonna import KDA. No, PCA. Next is we're gonna use the dimensionality of 2D for visualizations. So we're gonna say PCA, all right, and then PCA, and then N underscore components. PCC, CA. So let's say we'll see PCA with transform and like export. All right. So just like with the hierarchical this clustering, all you need to do is just fit it directly and transform the X bill. All right. And with that, we can go ahead to the next part, which is the figure visualization. So figure grid size. And then 0, 1, 0, 0. Let's see. Software. This is already the second column. And then Jeff. E cars, uh, school, since we're using the same cluster as in class. And then C map is variables as well. All right. PLT title PCA, two components, racing two components, PLT context table, principal amount or principal component one, and then PLT of file label, principal component, C, PLT dot show. Mhm. And see. Parentheses of flash like 12, which one? This is it's clapping. PCA, the transform. It's not, it's not understand. My last one. Figure. Hmm. Hmm. Makes us, let's go with 8 and 6. All right. Let's see. All right. So we have our PLT here. And let's see. Let's see all the points. All right. I think we can use this one. So let's see. Well, actually, I'm missing. If we want, we also need to check the variance ratio. We're gonna have to see the variance ratio, and then how to we need to access the uh, PCA, and explained variance ratio. Right, that's one. What else do we need? Let's see. We need to see as well what is affecting each component. What are the features that are in the component, right? What is giving it weight? So if we say ECA underscore components will assign here, we'll access pandas, data frame, and then let's see. We need the parameters. We need the PCA components here, components, and then columns will be for X, columns, and then index will be for PC1, and then PC2, uh, and then we can pick this one, and PCA. All right. Okay. Yeah, I think this is good enough. So what we have here now, let's go back to PCA components. So we're gonna say n is equals to because we only want to use two components for this one. Um, yeah. So let's see. All right. Uh, okay. So let's go ahead and explain the data that we have generated with PCA. So as you can see, we have the plot, we have the variance ratio, and we have table here, right? So this is the um basically how much each feature weigh for that specific component, right? Because each dot here, each placement of the dot here, principal component one and component two, is a representation of all the features that it has, right? Into that single dot, right? So um, it's plotting it there as a scatter plot. And then each one you see is a car, right? So if we say principal one, principal component one, we're gonna take a look at the different features. So we see if we were to put this in percentage, battery is around 8%. Um, this is negative 14%, 69%, negative 68. This is 7, and then there's a negative. So basically, this is in contrast with the total speed and the acceleration. So these two are the big things for PC1, right? Total speed and acceleration. So cars with high top speed and slower acceleration, right, will score high on the PC1. Why will it score high? Because these two are with the ones with the highest weightage, supposed to be. Um, so when it is trying to measure it, right, since these two are very heavy, right, it's gonna depend mostly on these two parameters to um, get a high score in PC1, right? So it's at the right side here. Cars that accelerate quickly, okay, but may not have extreme top speed, will score lower on the PC1, right? So it's towards the left. So we can say that PC1 here, what the algorithm did is this is basically a speed versus acceleration component, right? It's trying to see their difference through speed and acceleration. Now for principal component two, right? What we see here is what a small positive, strong positive, slight positive, negative, negative, or we can consider this negligible, 61%, and then a strong positive. So we have two, right? It's driven by horsepower and torque. So in order for you to high score in PC2, you're gonna have to have a lot of horsepower and torque. Now, when you put these things together, right, we can now say that the x-axis is for speed and acceleration. The y-axis is for, since we're dealing with horsepower and torque, we can call the y-axis as the engine power or how strong our engine should be, right? So that means if we go to the right, that we will have faster and faster top speeds, but lower and lower acceleration. As we go to the left, what we have generic or quick acceleration, um, but moderate top speeds. All right. If we go higher up, the engine and torque also goes up a lot. If we go down, then it's going to the more efficient cars. That's what it's trying to say. Um, let's see what else. So since we're using the data from k-means, right? So clusters, um, cars with the same color belong to the same cluster. So what else? Hmm, what else can we analyze from this? So it has some kind of trend, right? But this point in the middle is kind of confusing because it has a lot of separated data values. So we're gonna have to analyze that one first as well. Um, so we have the variance ratio, right? So what is the variance ratio? So whenever you hear this one, um this is the total variance in the data set as a whole, right? So what does this mean? It means that we have more than five. I think we are more than five. Let's see what else can we add here. Mm, yeah, I think that's all the key takeaway that we can get from this. Um, all right. So based on the scatter plot here, it's around zero, right? Where there's a separation, a distinct separation between going to this cluster versus going to this cluster, right? So the ones with yellow are obviously the cars with more top speed, better acceleration, and uh, or cooling, air cooling. So was it there? Oh, no, it's not there. But yeah, it's what we have here. What else do we have? All right, so I think that's it for PCA. There's nothing really more to add other than these things. What is making the PC more, you know, sensitive to distance? Like right now we can actually see the normal data. So that's good. Um, let's see. Okay. Any questions so far in how we arrived with this? Or is everything clear? So I hope you guys were able to produce this one as well on your end, just to be sure that it's working. All right. Let's go now to the last part, which is the isolation forest. So again, the isolation forest is used for detecting anomalies or the ones that are far from the group, the outliers. Okay. Now, in order to begin, of course, we're gonna have to import things from sklearn. dot ensemble. This is belong to the ensemble. And then import isolation forest. All right. So how does this one work? So isolation forest is uh let's imagine that we are randomly splitting our data and then doing decision trees over and over again. So whenever you do that, the data points are separated faster. All right, the outliers, the um what else? Because it actually just um pushes the outliers outside of the group, something like that. So the algorithm builds up many decision trees, right? And each tree will automatically and randomly split the data, right? Normal points take more splits to isolate because they win. Anomalies get isolated in fewer splits because they are already far away from the others. So they are very distinct when we see them on your data set, right? So uh, yeah, I think that's it for isolation forest. So we can continue now with the code. Let's save this one into something called ISO forest, and then isolation forest, contamination. We can also 0.1, random state, cars. This is ISO forest with small inputs. Also, okay. I think this is enough. We'll go ahead and do the scatter plot. So scatter and then X. Okay. And 0 and log 1. Let's see what else. After scattering, we'll have another PLT scatter here. Well, because that's Chicago, okay. Color green. So any outliers will be colored green. Also put a marker of X and then label as at what? Label outliers, right? After that, what do we do? We take care of the menu. So is it, we one agreement pipeline, um, say isolation first, and then be able to either show what else. Let's try this one first. Line 7 did not match that. Line 7. Done. Random state. Ah, yes. Bad operand type for area minus. So, a what's the problem? All right, so we need to actually call. Oh, no, no. Yeah, this is gonna slow. Almost there. Oh, no, maybe it's not it. Sorry, properly. Yeah. Okay, so I'm getting confused by this why it's not working properly. Might be able to plot this one. It's not coming out properly. Let me try this one out and say print. Hmm, okay. We'll try to get something out of this right now. Just after using the scatter plot. I'm trying to see if we can make it appear again on or business horsepower totals horsepower is capital P. Mm. All right, so if we use table format without actually taking a look at the visualization for now, we can see that these are our isolated anomalies. So there's a total of 120 rows of anomalies. Um, Based on what we have here for contamination is 0.1. So usually, 0.1, we are assuming that around 10% is an anomaly in our data set. That's why we're choosing 0.1. These parameters, again, with the other methods that we have, it's up to us to decide really what value we should put here, but it should be in decimal format, right? So percentage in decimal format. So in this case, I'm assuming that around 10% of it is uh, an outlier or an anomaly in our data set, right? So let's see. Eh, if we try and change this one to something higher, example, right? Then it's gonna be less sensitive to its criteria and choosing it for anomalies. And as you can see, we have more rows available now that it considers as anomalies. So uh, it really depends on what our factor is here. So yeah. Um, how does isolation force work within? So imagine, right, if your data is being randomly split again and again using decision trees. So decision trees from um the supervisory part, those kinds of trees. So the weird data points, right? The more that you use the decision tree, the more those data points will stick out, right? The more that they stand out. And with that kind of concept, that's how isolation forest works. So the algorithm builds many random decision trees. Each tree would split the data randomly. So each time that it splits, right? If it's a normal point, it takes more splits to isolate because they blend in with the data. But the anomalies, right? If you keep on splitting them up, they go further and further away from the decision tree, right? And uh, like what I said earlier, they stick out sort of when you take a look at it as a whole. So I can't really show you the graph for now. I'm not really sure why it's not working. It should work, but and I'll try to see what is wrong with it. So when I upload this file later on, I'll attach the correct code that will show you guys the correct uh correct visualization, the scatter plot. And let's see. Aside from that, there's nothing really you can get from this other than uh our restriction here. So you're just assuming that 10% of it is anomalies. So if 10% are anomalies, then we can consider these cars, these rows as the anomalies. So you can roughly see why they're anomalies, right? The car prices for this one, the horsepower for this, right? It's too big. They are very large. Um, let's see. I'm not sure if we can consider the car names and the company names, but uh, let's see. Horsepower. So I can't really say for these three columns, but I can say for the car prices and the horsepower. So I think it's taking a look at this part more. There's a wider difference between them. So the lower ones and then the higher ones. So those are the anomalies that it sees. All right. Um, yeah, I guess that's it. So if there's anything that we can improve on, it's this one. Again, I'll try to upload a complete code later on or tomorrow. After that, the data as well. I'll try to fix the data and then what we'll have is the corrected version. So if you remember, in our processing data part, we need to remove these ranges. So I'm going to be choosing the ranges with a higher value. So 12,000 to $15,000. I'm going to be choosing the higher one always. So for the horsepower, I'm going to be using the same thing, the higher one. So I'll try to if I can incorporate it in code, I'll try to incorporate it in code. And then so that you guys have also reference on how to do that using code. And then what else? I think those are the only things that we can need. I'll email you guys the requirements for the capstone project. So I'll let the admin know, and then they'll send you the email on what to do, how to do it, and what should be the expected output. All right. So yeah, I think that's it for today. Do you guys have any question? So it seems that one of your classmates didn't come back, but that's okay. This is recorded. Let's see. None selling. Not for now. All right. So yeah, apologies for some troubleshooting parts in our lesson. That's really unavoidable in programming, so that always happens. But we weren't able to solve it. Um, again, I'll upload it as soon as I can. And yeah, hope to see you guys again next week. Goodbye for now.
Thank you. Bye.
Welcome.